thick accent, but she's absolutely fantastic, as you can tell. It's just really, just very technical, and she's excellent. So I've watched a ton of her videos, and told students in the past about her, and she's great. It's all available online too, so there you go. Something to help you out. So for us, though, what I'd like to do is just go through a series of problems so that we can gain some comfort with what we're talking about, which is this method of sections, where we solve for these internal forces by cutting through at certain points. We want to be able to analyze these structural members in the future. We want to be able to analyze them at specific points, because those specific points are often these failure points, right? And we as engineers, we can take a very complex thing like a building or a bridge, and with some experience, it might take 20 years, but with some experience, you'll look at it and you'll be able to say, this and this member are the most important ones. I'm just going to analyze them, and I'm going to do a method of sections through them and figure them out and make sure that they're sized properly. And that is using engineering judgment to find the critical points in a structure. And nowadays, so those are the engineers that came out of engineering school all the way up into like the 90s. And then the engineers from the 2000s and 2010s have been using modeling software to do a complete analysis of every single structural element. So it's like for a bridge or for a truss system, they'll analyze every single member. But the older engineers, they have a different way of doing it. They target just a few members so they have a different methodology. They'll target just a few members, and then they can do hand calcs on those few members and stamp it and turn it in. And they're just as right. So you can see it's an experiential, it is a different way, a methodology that they were trained and that they've done their career. So it's really fascinating to see that. And the newer engineers are completely dependent on math models and software, and they wouldn't want to do it any other way. And you know what? There's some power in that, isn't that? Because you're analyzing every single member in the whole 100-story tall building. You know, it's just a different approach. Analyze them all, size them all, for multiple forces too. All right, let's move forward. So what I'd like to do is try to get one or two of these 6 problems. We can do it. Try to get one or two of those 6 problems done before break here. All right. So this one happens to be a torque problem. It's rotational only. There is no applied force that is in the X, Y, or Z. Instead, all we're doing is we're basically grabbing onto this crankshaft and we're twisting it, right? And the elements that we talked about are still true with this. So when I look at this end, and actually let's read it, shaft with smooth bearings loaded in equilibrium as shown. Wait a second, so it's equilibrium. That means this thing's not moving. All the forces in one direction add up to all the forces spinning in the other direction. In addition, these bearings on the end are not providing any resistance at all. They are allowed to smoothly rotate. So what that would tell me, if I look at point C right there, I would just by observation, if I take a cut through C and I look at only the stuff that's on this end, well, at A, it's a bearing that can just spin. There's no applied force at all past C. So at C, to be in static equilibrium, at C, it must have 0 torque at C. This is going to be interesting. Anyways, so at D, it's a whole different matter, because I got 400 Newton meters of torque spinning me one direction, and then I got 150 Newton meters of torque spinning me the other direction, plus another 500. Oh, wait, those two are in the same direction. Mm-hmm. So they add up to 550 Newton meters, and then it's spinning the opposite direction. So that way, this right here has probably the maximum torque at point E. Well, let's just walk it through one piece at a time. What's the internal torque at point C, D, and E? Solve for supporting reactions. Well, the first thing the first thing that they defined was that the bearings are smooth, so there is no supporting reaction. At A, its only purpose is that this crankshaft doesn't just fly out. It holds it in these collars, but it can smoothly rotate. And we're not applying any lateral load in the X, Y, or Z direction, no lateral loads. This is only torque load being applied to it, like just putting a torque wrench on it or something, just spinning it only, right? So that means there is, on this end, there is no X, Y, or Z load at all. Or then there's no torque either, because it's allowed to spin. So there's no torque on A or B. That's what I'm saying. By observation, smooth bearings, there's nothing going on there. For part C, let's solve for that one. I know that one's kind of trivial, but we should do it. So what I did is a free body diagram. I said, you know what, there is no torque being applied today, and the only, because there's no X, Y, or Z load on this end or this end, the only thing that we can have is a torque on this end, and since this torque is 0, in order to be in static equilibrium, we would have to have a 0 torque here as well. So look what I did. I defined going around this way as positive, and I actually sketched that. This is actually really important because we're telling other engineers, hey, look at my calcs. I decided that right-hand rule was positive. So if I put my hand, my right hand on this axle, if I put it in, I guess I'm going to go with my thumb this direction, so bring my hand underneath it. The way that my fingers curl this way would be the same as that. So I just defined basically my thumb going this direction as positive, and then my fingers curling in that direction makes this a positive torque. Well, it doesn't matter in the case of C. There's no resisting torque here, this reaction at this end, so there would be no applied torque here. It's 0. There's 0 Newton meters of torque at point C. However, once we get past this 400 Newton meters, it must be loaded somewhere in between C and D. Suddenly, point D, though, has something going on this end. If I cut through D and I look at just this end, what would that look like? Well, there it is. If I cut through where D is at, I've got 400 Newton meters. I know it's kind of hard for my sketch to show that, but I've got 400 Newton meters rotating in a right way, and then I have, well, at the cut, I have to have something that balances it, because nothing is balancing it over here. This is free to spin. So the only thing that can balance that 400 Newton meters is here at D. The torque at D must be in the opposite direction. So you see what I did? I wrote 400 Newton meters in the positive direction, plus 0 Newton meters on this end being applied to it, and then I have minus, because I define this as being a negative torque, a minus some torque D, which I don't know. Well, brought this over to the other side, 0 just falls out. If I bring that over to the side, it becomes positive. So torque D has to be 400 Newton meters to balance this. And it must be so. I've got an applied 400 Newton meters this way. I need to have a reacting 400 meters this way. Of course, this is reacting at the point where you took your section of that. So I could have chose the other side. I could have chose to model the other side, and I would have had 150 this way and 550 this way, would have got the same result. It was just simpler to do this side. So when I look at E, what would be simpler? Well, this side would be the simpler side to model this side, to do a free body diagram of anything to this right-hand side. Let's see if I did that. I didn't. I stayed with the same side. I did the more difficult side. All right, well, it's fine. It's actually good to see. So I went ahead and took my cut through E, and then I modeled this side only, did a free body diagram of that side only.
So at D, on step 2,
yes.
you show it going the opposite way so that it's in equilibrium,
yes.
which makes sense, but in the whole odd item, it has to be going in the same direction so that it balances out the torque on the far end.
But we're not exactly. And we are completely ignoring anything, after you take that section through there, we're completely ignoring the rest of it.
Okay.
So we know that this half, if this is in equilibrium, we know that this half of the axle has to be in equilibrium by itself.
Okay.
So if I have 400 Newton meters spinning this direction, I have to have 400 Newton meters spinning the exact opposite direction. For that piece all by itself, that section, to stay still.
Okay.
That's the cool thing about method of sections. You get to decide where you want to cut your section through, and then then you choose to look at one side or the other, and either side needs to balance separately. I don't think I've got one of these torque problems on the homework, so, but it's good to see it. So I looked at just the same left-hand side, but taking a cut through E now. So when I take a cut through E, right there, I ignore everything this direction. So I still have, I've got 400 going this way, and I have another 150 added to that going that same way. So when I sketch it, I know it's kind of hard to see which direction it is, but it's going this way, and I define that way as positive. So I'm going to have, and everything has to add up to 0, right? The summation of all the torques have to add up to 0 for this to be in static equilibrium. So I've got 400 in the positive going here, and another 150 in the positive going there, plus 0 on this end, minus this. This has to be going in the opposite direction to balance. All of that going in the positive direction. So minus tension, torque at E, torque, tension, so used to tension. So torque at E. So I have, bring this over to the other side, which makes it a positive, it's with the minus sign. I have 400 plus 150, 550 Newton meters. This must be 500 Newton meters of torque to balance the 150 plus another 400, 550 going this direction, positive. And incidentally, I could have done the other side. If I cut this and I look at just this side right here, well, I've got 550 newtons going this direction, and I would need to have 550 newtons going the opposite torque direction to be able to balance it. I would have got the same answer if I would have looked at just this section, this side, from that section. Okay, that torque one's kind of hard for me to sketch. I think I did a decent job of sketching it. So what's the internal torque at C, D, and E? There. That's what we solved by taking the method of sections and realizing, just like me and Jeannie were talking about, that we can just isolate and look at just the half or the other half. And it has to be in static equilibrium, just the half. Aha, now more classical shape. Actually, it's not truly classical because it still is like a crankshaft, but it's being loaded strictly in the vertical fashion now. Vertical or horizontal fashion. Actually, there's no horizontal at all, vertical only. There's no torque on this one. Still, if you think about it, when you have a crankshaft, there is typically a lot of vertical loads being applied to it very fast. You know, you're going a couple thousand RPM. You might have a lot of loads being applied to it very quickly. And the interesting thing about that is what's happening, say, at that collar. You know what, if I take a section at C, that's actually an important spot. I've got to make sure I have a collar right here that can handle the load that's being applied to it. Notice that if I did take a section at C, I would have this 2,500 pounds pushing down on the outside edge of that. Think of this as just like a cantilever beam, by the way, this little bit cantilevered out. And then this, think about it as a beam between two sides of basically a bridge, and a beam spanning. That's really how we're looking at this. And yes, we're using collars to support it. There's no difference. So what's being asked for? What's the normal force, the shear force, and the moment at section? If I took a section right through that beam right there, what would it look like on this end that's supporting it, basically? And then also do the same thing at point D, way over here. Cut right through there and see what you get. You know, frankly, it would be so much easier to look at just that side alone if I did that. And then over here, same deal. If I took a cut through there, it would be so much easier to look at just this side alone. But you know, I can't get moving until I figure out these reactions, because C has to be holding up something, and B has to be pushing up as well. There's nothing horizontal, but there's a whole bunch of vertical load coming down. C is basically holding up quite a bit. This collar has a lot more vertical load on it. This collar, I suspect, has a decent amount still, because there's a 3,000 pound point load pretty close to it. So I suspect B. I'm kind of curious to see which one of these, I think this one's gonna have a higher load. We'll see, right? We'll see. All right, so step one, right from our handout right here, step one is solve for the supporting reactions. So the supporting reactions are reaction at C, basically a vertical, and reaction at B, vertical. So what I did is I did a little free body diagram and acted like this was just a beam, and that these supports, I removed the sketch of them and I just put point loads on. Also, this distributed load, I just took, what's that, 12 feet? 12 feet times 75 pounds per foot, and I did a load right at the center. As we have learned in the past, a uniform distributed load can be modeled as a single point load at the midpoint, which would simplify it, right? And if it was like a triangular load, it would be 1/3 from the base, right? And these are just point loads. So I sketched it, well, 75 times 12 is 900, so, and I put it right in the middle, so 12 feet, so that'd be 6 feet over from that. So you're seeing, wow, 900-pound load, 6 feet over, 2,500 pounds, 6 feet over, plus 3,000 pounds, 12 feet over. It's some unknown reaction here and some unknown reaction here. This is a calc that you guys are familiar doing. Once you see that, you did calcs like that in statics form. Let's walk it through those. It has been a while. So, I wanted to figure out my support at collar A first. And I realized, since I have two unknowns, if I take the moment about B, the reaction at B, if it goes right through it, has a 0 moment arm, so it falls out. So that is one of those things that we can do to take two unknowns and simplify down to just one by taking the moment around where one of them is being applied. So that is why I decided, and notice that I showed this as a positive moment, in right-hand rule positive. Summation of moments about B. The reason why I took it about B is that force goes right through B, and if you take a force times a 0 moment arm, it's 0 and it falls out. All we're doing is we're looking at the moments about B. So what would that look like? Well, if I take the moment about B, you see that force is 2,500 pounds, and it is 20 feet over. It's 2 plus 12 plus another 6. So it's 20 feet over. So I've got 2,500 pounds causing a positive moment. Do you agree? If I put my hand right at B, if I put my hand, as if there was a z-axis coming out of the board, if I put my hand right at B like this, do you agree that that load right there would cause a positive curling? That would cause it to, you see the direction with my fingers are going in that direction where that 2,500 pounds is. So my thumb's coming out of the board, and it's the same as that right there. Right-hand rule, that 2,500 pounds with a moment arm of 20 feet, so that's why you see positive 2,500 pounds at 20 feet. Thumb coming out of the board. That is how I'm making decisions about whether it's a plus or a minus. This reaction at A is going the opposite way. Do you see how that, I guess what would that be? That would be counterclockwise, would be positive, and clockwise. This force right here is causing this to try to come around this way. And it has, what's it, 2 plus 12, it's 14 feet over. So that's why I put a minus sign in there. You said this right here, this reaction is causing a negative moment about B, and I don't know what the force is, but I'm going to be solving for it. So some unknown force times 14 feet, and it's causing a negative rotation. And then this 900 is causing a positive rotation. It's 2 plus 6, 8 feet over. This 3,000 pounds, it's pretty close, but 3,000 pounds with a 2-foot moment arm causing a positive rotation. It's trying to spin around this way. It's trying to take, if that reaction was not there, that would try to make this member spin this way. If it was bolted on right here, let's say. So there is my summation of moments about B equation right there. It must add up to 0. That's Newton's second law right there. all the forces must add up to 0. All the moments must add up to 0. In order to be in static equilibrium, it all must add to 0. And that's why we write it in this fashion. We say the summation of all the moments must be equal to 0. And we start with 0, and then we write our moment equation. So then I started multiplying it out. This times that, this times that, this times that, and add them all together, and I got 63,200 pounds. I still have this minus whatever reaction that is at 14 feet over. So I took this chunk here that was negative, and I brought it over to the other side, which makes it positive. And then I divided both sides by 14. The reaction at A, in order to keep this balanced, the reaction, that collar must hold up 4,500 pounds. That collar must do that, and if it doesn't, suddenly we're in dynamics, and this is moving, you know, and that's not acceptable. So we want this to stay in that collar. It's allowed to spin, clearly, because it's an axle, but it's not allowed to fall. It's not allowed to collapse. All right. So now that I know what that reaction is at A, I can take the summation of moments in the y direction, because all the forces also must add up to 0. All the forces in the y direction must add up to 0, because if they don't, we're in motion. All the forces in the x direction, and there's nothing. There's no forces in the x direction. So 0 is 0, right? But in the vertical, now I know what this reaction is. I know what this is. I know what this is down. I know what this is down. And I have only one other up to balance that. So what I did is I said the summation of the forces in the y direction, and I defined up as being positive. So for example, that reaction at A and that reaction at B are positive going upward. And so anything else going down is negative. So minus 2,500 going down, plus 4,500 going up, minus 900 going down, minus 3,000 going down, plus some unknown going up, some unknown reaction going up. So I took that reaction B, brought it over to the other side, and all of this, and it was a minus on both sides, so I dropped the minus on both sides. So, as I suspected, the collar at A has to hold up 4,500 pounds, and the collar at B is holding up just under 2,000 pounds. It's still holding up quite a bit, but the reaction at A, the collar at A has to hold up so much more. So, when you guys look at these huge machines, the electron dam down by Tacoma, and there was this huge axle that ran through, and you could see these collars that were around it, and some of the collars were larger and some of them were smaller. How do you think they decided that? How do you think the engineers calculated something just like this? They said, you know what, this collar is in the center, it has all these loads around it, that collar is going to hold up a whole bunch more, that's why it's so much bigger. And granted, back in the day, they did a lot of this by trial and error. They ran it for a while, they said, I don't know why, but that collar keeps going out all the time. That kind of stuff. It's true, they did a lot of that trial and error stuff. But they were very smart. They were practical engineers, they were field engineers, and they actually were very good with calculations. Basic algebra and trig, they were monstrously good, actually, at this basic statics. All right. They didn't have computers, so they had to be really good with it. All right, so what we just did is we solved for the external reactions, which is step 1. What's happening at A? 4,500 going up. What's happening at B? 1,800 going up. And I know the rest of these forces going down. All right, so now I can re-sketch this beam like this now. With forces going up, I can model it as something a little bit simpler. So, because they asked us, hey, what is the situation if you take a section at C? What's the situation if I take a section at D? What's happening to that material, that round axle, right? How much does it have to resist? So that's my part 2, is I'm going to do a free body diagram at point C, because that's what they asked for. Hey, what's happening right here? It actually is just to the right of bearing A. So to the right of bearing A means we get the force at A, the 4,500 pounds going up is part of it. So we're including that collar and the force that's happening there. So when I sketch up my model of just that left-hand side, because we're doing method of sections, we don't need to look at the whole thing. Let's just look at that side only. And so what's happening at C? Well, I've got 2,500 going down, and I've got that collar pushing up, 4,500 pounds pushing up. Then using their sign conventions. I sketched these onto that. Then we're going to go ahead and solve for the shear, we're going to solve for the moment, and we're going to solve for this normal force. I looked at it and I said, you know what? That normal force at C is 0 because there's nothing else going on horizontally. It has to be 0. And at this point, you guys you did your sophomore statics, perhaps, not all of you guys, but so you guys transferred in. So sophomore statics, and you've also taken statics 1. And I always told you to calculate everything, but at this point, there's some things that you can just state by observation, or if it's even simpler, you could say it's just trivial. I mean, it's just there. In fact, they answered it. The sketch answers it. So I think it's just fine for you guys to start using by observation. This is what you're going to see on engineer's calcs. When something is extremely simple that you don't really need to go through a whole sheet of calcs, I'll just say by observation, because I can see it. Any other engineer can see it. If you say something is trivial, any non-engineer can see it. If you say something is by observation, any engineer should be able to see it. That's the standard. Trivial, just nothing, right? And then by observation, it takes another engineer, the average person walking down the street can't just see it like us engineers. So by observation, I look at this and I say, you know what? There's no other force horizontally. So that normal force has to be 0 by observation.